The distances separating the stars are so enormous that it is even difficult to imagine them. Suffice it to say that taking as reference the average separation between the Earth and the Sun, the so-called Astronomical Unit, AU, equal to 149.6 million kilometers, the distance that separates us from the nearest star, Proxima Centauri, is 266,000 times greater. That is 103 million times the distance from Earth to the Moon. Even a ray of light, which moves at the maximum speed allowed by the known laws of physics, takes 4.2 years to reach us from Proxima Centauri, while less than 8.5 minutes is enough to fill the space that separates us from the Sun. In these numbers, in their relentless inevitability, is enclosed the problem of interstellar travel. If we then take into account the dimensions of our galaxy, about 100,000 light-years in diameter, and those of the observable universe, more than 10 billion light-years, the question of trips in the deep cosmos can only leave us dismayed. Nevertheless, especially since the 50s, several scientists have accepted this exceptional challenge, facing it with great passion and extraordinary inventiveness. Of course, the problems to be solved were and still remain enormous, but there is one thing that not everyone knows. The first interstellar journeys, however rudimentary, have already begun. At this moment, there are space vehicles that have already gone beyond the known boundaries of the solar system. These are the automatic probes launched by NASA for the exploration of giant planets, and thanks to the trajectory chosen for their mission, they have gained enough energy to escape permanently from the gravitational grip of the Sun. The first to leave the Earth in 1972 was Pioneer 10, destined to fly over Jupiter. The last signal received was on January 23, 2003, when it was 80 UA from the Sun. At the moment, it is 122 UA away, and at a speed of 12 kilometers per second, it is heading towards the constellation Taurus. It will pass relatively close to a star in 2 million years, but at that point, it will be only an inert wreck. In the extremely unlikely event that the probe is detected and recovered by an alien civilization, it will tell its story through the famous gold plate on board, designed by Carl Sagan and Frank Drake. The twin Pioneer 11, launched in 1973 to Jupiter and Saturn, ran out of energy at the end of 1995 and has been silent ever since. But it also carries on board the gold plate, and in 4 million years, it will pass in the vicinity of a star of the Eagle constellation. The two other messengers of humanity among the stars are the automatic vehicles Voyager 1 and 2, both launched in the late summer of 1977 to explore the systems of Jupiter and Saturn, and in the case of Voyager 2, also those of Uranus and Neptune. They have brilliantly surpassed all the most optimistic forecasts of their operation, so much to reach and exceed the boundaries of the heliosphere after a journey that lasted tens of years. The two Voyagers have sufficient energy and propellant reserves for attitude control to ensure their operation until about 2025. But even as dead, the two probes will continue their unstoppable journey through the stars, moving away by 3.5 UA per year on Voyager 1 and 3.1 UA per year on Voyager 2. In the remote but always possible eventuality that during their wandering through the galaxy, they will be intercepted and studied by an extraterrestrial spaceship, the two Voyager also carry on board a message of ours, a golden copper disc, 30 centimeters in diameter, containing a phonographic recording of images and sounds, chosen to represent us and our planet. Each disc is housed in an aluminum case together with a reading device. On the case, in pictorial form, as in the Pioneer plates, explanations are given about the nature of the spacecraft and how to decode the information recorded in the disc. But even in this case, the message represents more than anything else our inalienable desire to defy death, entrusting a part of our culture and our world to eternity. At the speed of the Voyager, representative of our current technological capabilities, it would take 76,000 years to reach the nearest star. This duration would be totally incompatible with any reasonable form of interstellar travel currently conceivable. Even using completely autonomous robotic probes, it is difficult to assume that all onboard systems can continue to function for such a long time. But even if this were to become technologically plausible, would we be able to invest the enormous human and material resources necessary for an enterprise that only some of our very distant descendants might enjoy? So the first obstacle to overcome is represented by the enormous distances that separate the stars. This little data is enough to understand that we need technologies completely different from the chemical propulsion used by New Horizons, Cassini, Voyager, and countless other probes to make an interstellar journey in times compatible with human lifespan. Ionic engines like those used in the Deep Space One and Dawn missions are not good either, because they build their acceleration with exasperating slowness. Instead, you need systems capable of accelerating a spacecraft to a significant fraction of the speed of light in no more than a few years. For interstellar travel to become attractive for human beings, triggering that cocktail of aspiration, ambition, curiosity, and competition that motivates our greatest feats, we should significantly increase the speed of travel. An acceptable value could be between 5% and 10% of the speed of light, c, but certain missions could also be conceived and carried out with a speed of just 0.01 c. A possible solution to this problem was proposed in the 70s of the last century by the Daedalus Project. Under the aegis of the British Interplanetary Society from 1973 to 1978, a group of engineers developed the construction schemes of a giant spaceship as tall as a skyscraper, weighing 54,000 tons, to be built in orbit around the Earth. The spaceship, powered by a futuristic nuclear fusion engine, would have been able to reach a final speed of 0.12 c, 36,000 kilometers per second, and to reach, after 46 years of travel, Bernard's star 6 light-years away. Daedalus did not have a human crew. It was expected that after about 25 years from departure, 2 5-meter optical telescopes and 2 20-meter radio telescopes aboard the second stage of the spaceship would start automatically scanning space around Bernard's star, looking for possible planets to photograph and analyze with spectroscopes and other scientific instruments. But the project was too ambitious and expensive, so it never passed from the ideation phase to the realization phase. The technical problems to overcome were immense, starting with the need to obtain large amounts of helium-3, which together with deuterium was the main ingredient of the mixture needed to feed the hypothetical fusion engine. So the project was abandoned, leaving the dream still unfulfilled of the interstellar journey to the following generations. Daedalus was in practice a giant automatic probe, and putting men on board would have been enormously more expensive and complex, involving scales of mass and energy from thousands to millions of times greater. Yet even these scenarios have been explored, up to give birth to the idea of the Interstellar Arches, gigantic ecologically self-sufficient habitats able to wander for thousands of years among the stars, while countless generations of men, animals, and plants follow one another inside them. In practice, huge space colonies destined to be launched into interstellar space, even at modest speeds less than 0.01 c. Although it may be difficult to imagine why humans should undertake a journey knowing for certain that they would never reach their destination. In any case, in those same years, the American physicist Robert Bussard proposed an original way to solve the problem of the enormous amount of propellant needed to sustain speeds equal to a fraction of the speed of light. Thus was born the concept of the interstellar ramjet, a vehicle able to collect during the trip the hydrogen present among the stars to exploit it in a nuclear fusion engine. But apart from the problems presented by the realization of the engine, the collection of interstellar hydrogen would be far from simple. Assuming an average density of 1 atom per cubic centimeter, to collect 1 kilogram of hydrogen traveling at a tenth of the speed of light, it would take a funnel with a mouthpiece of over 5,000 kilometers in diameter, and the collected matter would be negligible compared to propulsion requirements. For this reason, interstellar ramjets in the various versions proposed are not considered physically feasible. The space engineers have then taken another direction, going from the gigantic to the very small, starting to design missions conducted with intelligent robotic probes, miniaturized beyond any limit currently conceivable and able to travel at 0.1 C. In practice, they started to think about the possibility of using the so-called probes of von Neumann, that is to say of automatons that once arrived at destination would be able to build with the available raw materials copies of themselves. Having successfully completed the exploration or colonization of a world, von Neumann's probes could start new automata to other star systems to repeat the enterprise. Fractal colonization of space, therefore. But we must admit that with these scenarios, we are unfortunately more in the field of science fiction than in that of realizable technology. Since then, no great progress has been made. But in the meantime, something has happened that has changed the cards on the table. That is the discovery and precise location of extrasolar planets similar to the Earth around other stars. Almost all the projects we have just described date back to a time when nothing was known about the actual existence of planets around other stars, let alone their physical and orbital data. This certainly did not make it very easy to find attention and economic contributions for those who proposed to build huge and very expensive spaceships and then send them to stars of which we knew practically nothing. It would have been too big a gamble to go blind with such expensive missions, and therefore unrepeatable in case of failure. Things started to change after 2000, however, when in a few years thousands of extrasolar planets were identified, many of them of terrestrial type, and orbiting within the habitable region of the star. A turning point then electrified the entire scientific environment, giving engineers new motivation to design missions capable of reaching the nearest stars. The only and eternal problem remained that of distances, which, although astronomically small, were still too big for our technological possibilities. It would have served the discovery of a planet of terrestrial size, habitable, but also distant not more than 10 light years, which seemed decidedly difficult, given that the stars so close together can be counted on the fingers of one hand. But in April of 2016, astronomers came out with perhaps the most important astronomical news of recent years. Discovered in the habitable zone of Proxima Centauri, the nearest star to us, a rocky planet a little larger than Earth. It's called Proxima b. It was hard to believe, but a planet suitable to host life had been discovered right in orbit at Proxima Centauri, the nearest star to Earth. It was a dream come true at last. In the second part, we'll see what an extraordinary space exploration project has given birth to this discovery, and how you're planning to visit the planetary system of Proxima Centauri to see if Proxima b is a planet suitable for life.